Welcome to the fourth session of our lecture series on superconducting resonators. This series is brought to you by the NYU Nanolab, the Laboratory for Quantum Materials and Devices. We would also like to give special thanks to the Nord Tech Hub and the Microelectronics Commons for making this lecture series possible. This is a short session focused on deriving the input impedance of transmission line resonators near resonance, which will let us establish their equivalent lumped element RLC models. Our objectives for this session are twofold. First, to derive the input impedance of transmission line resonators near resonance, and second, to use that result to identify their equivalent lumped RLC models. Let's start with a quick recap from our previous session. A transmission line resonator is simply a section of transmission line with a specific length, L, and boundary conditions, either open or short circuits. We saw that there are two main types: half-wavelength resonators, which can have both ends open or both ends shorted, and quarter-wavelength resonators, which always have one end open and the other shorted. Like any transmission line, these resonators are also characterized by their characteristic impedance, phase constant, and attenuation constant. We start this session by obtaining the input impedance of a transmission line terminated with a short to the reference. This is the general expression for the input impedance at a distance L from the load of a lossy transmission line terminated by an arbitrary load ZL. For a short-circuited line, ZL equals 0, which simplifies the expression to this single-line form. Using the identity for the hyperbolic tangent of a sum, we can rewrite Zin as shown inside the red rectangle. Finally, by multiplying both the numerator and denominator by minus j cotangent of beta L, we arrive at an alternative form for Zin. These two equivalent expressions for the input impedance of a short-circuited transmission line will be useful in our upcoming derivations. Now let us use the expression we just derived to evaluate the special case when the frequency is close to resonance. To do this, we first define omega as omega 0 plus delta omega and replace beta by omega divided by the phase velocity, since we are working with TEM waves. We will also assume a low-loss transmission line, which means that alpha times L is much smaller than 1, so the hyperbolic tangent of alpha L can be approximated by alpha L. Under these conditions, the input impedance of the short-circuited line simplifies to the form shown in the red rectangle. On the right-hand side, we also show the equivalent expression using the cotangent. We will now use these simplified expressions to derive the input impedance for both the short-circuited half-wavelength resonator and the quarter-wavelength resonator. Let's start with the half-wavelength resonator. At resonance, L equals lambda over 2, and lambda is equal to the phase velocity divided by the frequency. Therefore, L equals the phase velocity times pi divided by omega 0. When we substitute this value of L into the expression for the input impedance of the short-circuited transmission line, the argument of the tangent reduces to pi plus delta omega pi divided by omega 0. Since delta omega is small, we can approximate the tangent of pi plus delta omega pi divided by omega 0 as simply delta omega pi divided by omega 0. This leads to the compact expression for Zn shown in the red rectangle. Notably, this expression for Zn is in the same form as the equation of a series RLC lumped element resonator operating near its resonant frequency. Following a similar analysis, we can determine the input impedance of the quarter-wavelength resonator near resonance. This time, however, we start with the expression for Zn that uses the cotangent rather than the tangent, which avoids an undetermined solution. We again substitute L into the expression, and from there, we find that the input impedance is equal to the expression shown in the red rectangle, which resembles the input impedance of a parallel lumped RLC resonator. We have found the equivalent RLC circuit models for the quarter-wavelength and short-circuited half-wavelength resonators. but the open-circuited half-wavelength resonator is still missing. To analyze this case, we start by deriving the expression for the input impedance of a transmission line terminated in an open circuit. We return to the generic expression for Zns of a lossy transmission line terminated in a load. This time, however, we make a twist. We replace the impedances with their corresponding admittances to obtain the expression for the input admittance, shown in the red rectangle. An open circuit means that YL equals 0, so the input admittance expression reduces to this single line. Then, we return to the input impedance and apply the hyperbolic tangent of a sum identity to obtain the expression for the input impedance of an open-circuited transmission line, shown in the red rectangle. Then, as in the case of the short-circuited transmission line, we derive the expression for Zin at a delta omega. Assuming a low-loss transmission line, this results in the expression shown in the red rectangle. Finally, we apply this expression to the case of a half-wavelength resonator, whose length at resonance is equal to half the wavelength of the signal it operates on. This brings us to the compact expression for the input impedance near resonance, shown in the red rectangle. As you may have already noticed, this is equivalent to the expression for a parallel lumped RLC resonator. Putting it all together, near resonance, half-wavelength resonators with shorted ends behave as series lumped RLC circuits. Half-wavelength resonators with open ends behave as parallel RLC circuits, and quarter-wavelength resonators also behave as parallel RLC circuits. From these expressions for Zn, we can derive the values corresponding to R, L, and C in the transmission line resonators, and then use the lumped element formulas to calculate parameters such as the internal quality factor. In future sessions, we will also see that these equivalent models are used to extract resonator performance data from device measurements. That wraps up the transmission line resonators part of our lecture series. In the next session, we will introduce the coplanar waveguide geometry. Let's quickly review what we learned in this Lightspeed session. First, near resonance, the behavior of Zin for transmission line resonators follows the same pattern as series or parallel lumped element resonators. Second, this means we can match transmission line resonators to equivalent RLC models. And third, open-ended half-wavelength resonators and quarter-wavelength resonators behave like parallel lumped RLC resonators, while short-ended half-wavelength resonators behave like series lumped RLC resonators. Thanks for watching. See you in the next session.